It's sharing.
Hello, everyone. So, welcome to the ARC seminar for today. We'll have Ryan Seymour.
Hello.
Hopefully, so Ryan, can you hear us?
Yep, it's all good.
Okay.
Cool. Hello, everybody. I'm Brian. You guys all know me, I guess. I work with Yonbe. I guess. I do various things, but I do testing GR, and I have a project on effective one body, and it's always in the literature. So I decided I would make a presentation that discusses how it works, and maybe it will help people to understand why it works. Since there's like a lot of waveform models, it's very easy to get them all confused if you don't do parameter estimation. So yeah, anyway, okay. All right, so the way this talk is gonna be structured, I'm gonna introduce the two-body problem in Newtonian / GR, and then discuss how does the conservative, how do you, oops, sorry, how do you write the conservative dynamics for a test particle in space-time? And in part 3, I'm going to add dissipative effects and then conclude. So I guess, right. So everybody knows that in the Newtonian gravity, you can convert the problem of two masses with like two momentum and locations into the center of mass frame, and then you write it with the relative momentum and the total momentum, and then it turns out you can solve this in the standard way. And the cool thing is you can generalize this for general relativity by doing it perturbatively. And approximately what it actually looks like is it looks like a test particle orbiting like a deformed Schwarzschild metric. And we'll discuss what that means later. And then you can obviously calculate gravitational waves for this. So, okay, so here's a plot that you guys have probably all seen where depending on how compact the system is or what the mass ratio is, right? So on this is basically like what is the typical velocity of the system. And then on this axis, it's can you expand about the mass ratio, right? And so with post-Newtonian, you're saying that the velocity is really small and that it's moving slowly. For self-force, you're saying that the background geometry is a Schwarzschild black hole. And then numerical relativity, you make no assumptions, but you just do a lot of computation. And I guess like the thing that I want to ask the question of is can post-Newtonian theory be improved by the boundary condition of kind of like the self-force boundary condition? Because basically, if you're like in this region, then these two, you can compare these two and see, do they agree? Yes. So, okay. So basically, okay, here's a bunch of typical ways to compute the trajectory in the two-body problem, right? So you can do this post-Newtonian or like post-Minkowskian, and you're expanding about V over C, and generally this is analytic. Well, it's analytic if you say it's quasi-circular, and most of the time it's probably going to be an ordinary differential equation. And then you compute the time domain waveform or a time domain trajectory, and you can convert it to a frequency domain waveform, right? And yeah, and then using the stationary phase. That's how most of them work, right? And then you do perturbation theory where you're linearizing the Einstein's equations to look like a 2 + 1 PD, like PDE, and you can solve that. I guess a lot of times it's with separation of variables. If you're doing an Emory, you probably can't do separation of variables, and then somehow you're probably going to be solving a 2 + 1 PDE. But it's a lot easier because it's linear. Numerical relativity, basically there's no assumptions, and there's just a nonlinear PDE that's hard to solve. And then I also include you can also do like this effective field theory or amplitudes, and you're saying that the gravitational constant G is small, and it's and I think I'm pretty sure that this is more accurate for unbound orbits, but I think it also is slightly more accurate than black hole perturbation theory if you are highly eccentric. So I put a question marks. I don't really know the numerical method that people use to calculate those. So yeah. Okay. Yeah, right. And then okay, so obviously this is what the waveform looks like. You have the in-spiral that's quasi-circular. And then there's a plunge, which I will discuss what I mean by the plunge later, and also the merger, and then also the ring down. And I'm only going to be talking about the first half. No ring down. Okay. Yes. Okay. Oh, yes. And then okay. So now if we restrict ourselves to comparable mass systems, what are some like typical waveforms that people use? So there's this Taylor F and Taylor T. These are just if you use the post-Newtonian calculations, and you can just do pen and paper and then have enormous expressions, and you can write them down, and then people put those in all the software packages they use. And so right, it's the in-spiral only, it's fast, and then basically all the other approaches are kind of based on this for the approximates. The Phin-X family is most of the time these are just a frequency domain waveform, because generally you want it in the frequency domain at the end of the day. They're fast and they're good for parameter estimation. I think that kind of like what people are doing with these though is they're picking a bunch of kind of like a phenomenological waveform that they're just like picking like an amplitude and a phase, and then kind of picking it ad hoc, and then trying to pick it in a way that will agree within our simulations. And so like they're really fast, and that's, I think most of the time the PE is done with these. But yeah, the question is how do you pick the right assumptions for what the amplitude and phase look like in the frequency domain? And I think that's so yeah. And then so basically the effective one body, it's a time domain. It's more accurate than Phin-X, but it's at least probably 10 times slower, I think. And so it's only really used in parameter estimation for like stranger systems where maybe the Phin-X is not calibrated as well. Yes, and the numerical relativity is incredibly slow but very accurate. And then surrogate model is you just are basically doing machine learning in our data. These are really fast, but they don't generalize out of sample very well outside of the training data. Yes. So yes, and then okay. Oh, and then I have the nomenclature in case anybody ever sees these long waveforms that are in the literature, right? So right, so it says IMR Phin-X PHM in our title. Basically, what it means is in-spiral merger ring down is the brown, and then spin precession is the P, and then high order modes is HM, and then neutron star tidal is blue, or and cyan. And then and then maybe this would be like this could be EOB instead of Phin-X or whatever. So yes, yeah. Okay. Okay, so now let's go to what does the post-Newtonian two-body problem look like if you expand it about like basically m times f. And so the binding energy, looks like this expression, right? Oh, I guess there's no laser in this. Oh, it's the center one. Okay, right. This is the binding energy. This is the gravitational wave luminosity for I'm assuming circular orbit. And then the way you calculate the trajectory is you just solve the system of ODEs, right? Yeah, and like this is how you calculate the Taylor T and the Taylor F types of waveforms. Yes. And then I think the thing to look at though is the interesting thing though is for Schwarzschild, people actually know what the binding energy looks like, and it looks very different than what the PN calculations are, because it has a pull at the light ring. You can see how this 3, right? So if you keep adding more PN terms, it's not going to converge to that pull because you're kind of unable to. So I think the question is how can you find a good resummation method that will capture the effect of this light ring where basically yeah, right, because the energy goes to like negative infinity, or sorry, right? Okay, yeah. Anyway, basically it becomes like the energy grows a lot faster near the limit. And right, so this motivates some method to resum this effect. Yes. Okay, yeah. All right, I'm gonna go to the next section now. Oops. Okay, now the conservative dynamics for a test particle. Okay, right. I'm gonna start out by just reminding everybody about how to write the geodesic equation with Hamilton's equations, because it's not exactly clear, when you just look at it. Because so the action is like the integral over the path length, and then the path length is just the normal one. And the key thing is we want to decompose it into like a 3+1 split and have a preferred time. So yeah, and then so generally, like for any parameter like sigma, this is what the action looks like. And then you can like figure out what the conjugate momentum are. But the weird thing is, right, when you look at this, like you get a zero Hamiltonian. And then the question is when you go back, you're like, how do I compute Hamilton's equations with a zero Hamiltonian? Yeah, so the key thing is there's what's it called? The parameter space is actually constrained. And so the reason you get a zero Hamiltonian is you need to take this into account. In general, it's you have to be very careful when you do this. But luckily for us, it's actually very simple what the constraint was. It's actually just that that they need that it's like the forward velocity is -1, or like p squared is -1, right? And so the question is how do you actually get this constraint to agree? And so basically what you have to do is you have to add a Lagrange. The Hamiltonian and now gets an extra Lagrange multiplier, which is like this lambda, and then it's basically this p squared plus m squared, and then I just removed like the like you can't switch, like if you start out on one of the if you start out as a time-like momentum, you can't like switch to a space-like momentum. So we're only thinking about time-like momentum. So I'm just going to throw away the space-like momentum piece because there's no way to jump between those two, right? And then now you can actually just if you compute what the Lagrange multiplier is, it's basically just this dt d sigma. Yeah, I should have had a sigma, but anyway. Yeah, anyway, so basically, and then right in this equation right here, what I'm saying is right now this is not equal to 0 anymore, because now that the constraint was taken into account. And so this H3 that I call is actually now what the Hamiltonian is for the geodesic action. And it's the solution. It's basically like the p sub t or minus pt if you solve p squared equals -1. So so basically if you look at the mass constraint or the mass shell constraint, it tells you what the Hamiltonian is for this. Okay. Yes. Okay. So now we're going to think about how it works for the case that there's two particles. And so say you have two mass constraints where there's like p1 squared is equal to -1 m1 squared, and p et cetera for p2. The question is how do we switch the frame correctly in general relativity? Right, and then so obviously the first one you want to do is right. Your total momentum is just the sum of the momentum. And then one thing that works is your relative momentum. You can just define it as basically the time piece is just the dot product between the two. Okay. So you have to pick p1 is equal to, okay. One thing I forgot to write on the slide is basically like the vector p1 is equal to minus vector p2. So you have to pick this frame. And then if you pick this frame, you can define the relative momentum kind of in a useful way here. Yes. And then the question is what is like the mass shell constraints for the relative momentum and the total momentum? basically, I wrote it what it was for the total momentum right there. And then the key thing to realize though is that this I'm gonna talk about this H real and H injective a lot during this talk. So basically the real Hamiltonian is just the negative of like the timepiece of the total momentum, and then the effective Hamiltonian, it kind of encodes the relative motion. Yes.
You said that you choose the frame such that P1 is minus P2.
Yeah.
That makes the total momentum 0 on your second bullet.
P0. Oh, you're saying this is equal to 0?
Or
no, which one?
In the second line of your second bullet, you have just P mu equals P1 mu, P2 mu.
Yeah.
Wouldn't P mu then be 0?
No, sorry, it's only the spatial ones are 0.
Oh, only the spatial.
So yeah, so so the time part is.
Oh, okay.
I think the time part is just, I think it's m1 plus m2 squared. Yeah.
Okay, so these are all spatial.
Yeah.
Oh.
Yeah. So sorry. Yeah. So if I had a mu, it was I'm using mu for 4 vector and then I for 3 vector. Yeah.
Okay.
Yeah. Like, oh yeah, it's kind of confusing because I guess this is P1 lower subscript mu. It can try to with P2 mu. I realized this. I guess this comma looks weird, but yeah. So this is the timepiece and then this is the spatial piece. Yeah.
Okay.
Yeah. Yeah, and like I'm kind of like motivating this form. It's kind of subtle to figure out how to motivate the form correctly. Like there's a lot of methods. I just picked a simple example to do this, but yeah. Yes. So basically by switching the frame and using these new mass shell constraints, it kind of generalizes how to do this how to do the switch to the center mass frame for in the relativistic case. Okay, so and the cool thing is actually that the real Hamiltonian is related to the effective Hamiltonian, right? And so basically like it's plus p the vector p squared, right? And the key assumption that we're going to make is we're reducing the phase space so that the center of mass doesn't move, which is true until like the merger, because like during the thing is the center of mass I think moves kind of like circles a little bit at each time for the gravitational wave, but on average it stays at the same point until it gets the final kick, because it only maybe like only half the final cycle happens until it merges. So that's anyway, so that's the key assumption. And then so now okay. And now what you want to do, I don't think oh yes, okay, yeah. So now, is there any more questions? Okay. So now the question is how do we match this Hamiltonian? Like what we want to do is we want to match H real to something that we can physically understand. And so what I'm going to introduce is this effective metric with that looks like the Schwarzschild metric, because it's a diagonal metric just with extra coefficients, this A and this D and this C, that will encode the extra symmetric mass ratio dependence, where eta is like the reduced mass divided by the total mass. Or sorry, I meant to say nu, but yeah. But basically, we're going to figure out what this A of R and C of R, and and then the other thing that gets adjusted is the mass shell constraint gets slightly changed, but that's this with this Q. Well, so it's not exactly geodesic motion in the effective spacetime, but I'll discuss this. Yeah. Yes. Okay. So and then it turns out if you do the analysis, you can use gauge freedom to fix C is equal to 1, and basically that Q only depends on the radial momentum. And Q is going to be a 3pn effect. These A and D's will be like lower pn. So at first order, it's approximately just a deformed Schwarzschild geodesic. Okay. Yes, right. Okay, now I'll remind you guys. So the 2pn center mass Hamiltonian is very complicated. I'm going to be doing this to 3pn, and you'll see how much simpler it is when I rewrote it in this this different form, right? So yeah, so basically like the 3pn Hamiltonian is about like twice as long, and it cut off. I couldn't put the 3pn, but anyway, basically it was on another page because it was too long. Anyway, so okay, so now the thing is I can write the 3pn Hamiltonian like in this form, and it actually is much simpler. So right, because I'm just, okay, so right, so the if I'm matching H real to H, I'm matching this H real to this H ADM. And that's how I'm figuring out what these A and D terms are. Yeah. So yeah, right. So then basically like the only thing, like the things that get changed, right? So the effective Hamiltonian just looks like this, where there's these functions that I defined down here. And this U is just M over R. And so right. So and the key thing to see is this A of U. This is like the Schwarzschild, right? Because it's 1 minus 2m over r. So this, but by doing this matching, you can enforce so that it looks like Schwarzschild approximately, right? And also there's no 1pn effect in the there's no 1pn modification. So up to 1pn it actually is just Schwarzschild. At 2pn order, this where there's this u to the third. There's a 2pn effect to the in this effective metric, and yeah, and right, this d bar has this. This is actually I moved the coefficients over so that you can line them up so that basically like this one corresponds to the u squared, and then this u squared is the u third. Anyway. Right. So yeah. So basically, this is a 1pn or sorry. This since oh sorry. Okay. So D enters at 2pn because it enters as D times PR squared. Anyway. So yeah. That's why the 1pn match. That's why at 1pn is still Schwarzschild. Yeah. Anyway. Yeah. And then this Q is like a 3pn effect. Yeah. So the mass it's geodesic until 3pn. Okay. Yes. Yeah.
Can I ask the next question?
Sure. Yeah.
So it looks like when nu is 0, that's the test particle limit.
Yeah.
And it looks like when nu is set to 0, then at 3pn all of the like the GR terms are all 0. Right?
Yeah.
But what order does GR actually matter in the test particle limit in PM?
I don't. So I think in the test particle limit, it would just be a Schwarzschild hole. So yeah. So it should be that they all are at least proportional to nu.
Oh, I see. Yeah. I see.
Yeah, because like. Yeah, basically because we're doing the matching, we're making it so that all the new effects happen at higher RPNs. Yeah.
Okay.
Yeah. So anyway, yeah, people do these computations and also have done it to higher orders. It starts becoming much complicated at 4pn, so I didn't include that because I think like when they say they have the 3.5pn Hamiltonian, maybe I think they have the 3.5 Hamiltonian, but maybe in like the circular limit they know the 4pn one. So I think that's why they know EOB to 4pn. But anyway, yeah. Yes. Okay. So conclusion, right? So the conservative dynamics of the two-body problem look like up to 1pn are just the Schwarzschild motion in an effective spacetime that's like a Schwarzschild black hole, and then at 2pn it's just you deform the metric by the symmetric mass ratio with some effective metric, and then at above 3pn you have a deformed metric and also non-geodesic mass shell terms. Yeah. Okay. So part 3, dissipative effects. Yeah. Okay. So yeah, so up until now, I was only thinking about conservative effects, and we need to add the effects of radiation reaction after the fact. And right, so we know that gravitational waves carry energy and angular momentum, and then we need to figure out where how to add terms for dissipative effects to the equation of motion. Oh yeah, because I don't think I wrote it earlier, but this, like, the way you would actually figure out the trajectory of the particle would be just by solving ODEs with computers, right? And so you can directly compute what these are in terms of Anyway, basically, like, what I'm doing is I'm adding these generic functions, this fr and this fi, and we got to figure out what are they. Okay, so yes. I guess. One thing that's very interesting when you're thinking about dissipative effects is the question of why does a point particle merge? And so the key thing is this is the effective potential for a Schwarzschild black hole. And you can see that basically there's an angular what's called the angular momentum barrier to the left, and then wherever this is flat is where the particle lies. So yeah, and so I think I think I should have. Okay, anyway, sorry. But basically, like, my point is as gravitational waves radiate the angular momentum, this angular momentum barrier gets destroyed, and then what actually happens is at some point the conservative motion actually causes it to plunge into the black hole. And then anyway, that's why I think it's the merger. The merger is slightly different than the inspiral up until that point, is because when you're radiating, like, the inspiral is dominated by this gravitational radiation, but the merger is caused by the loss of this barrier and the plunge into the black hole. So that's anyway, that's why the binaries eventually merge. Yeah. Okay, so now let's actually calculate how what f sub r and f sub I are. And so you can just compute what the Hamiltonian rate of change looks like. And anyway, basically the long and short is, right, it just looks like r dot times fr plus phi dot times fi. Yeah. And so yeah, so for non-circular orbits, the energy, you want to use angular momentum and energy balance laws, right? And they become a little bit more complicated because remember how I was talking about how the energy only really, like, the reason that kicks happen is because the energy, like, as the particle's going around the black hole, at any instant it might be emitting more gravitational waves in one direction than another, so it's violating kind of like the angular momentum is being lost in different directions at each time, but the thing is on average it's basically just still as a circular orbit. And people have figured out how to incorporate this effect for, if you wanted to, like, write your model for an eccentric orbit, you want to have, like, these, like, shot terms, which is basically it's basically like if you have your binary, inside your binary, like, you know how to calculate how its trajectory is, but when the waves scatter off the waves, I think it's called the near zone, right? Basically, like, in this zone right here, things will, like, the waves will scatter and affect each other. And this is related to the fact that it doesn't the energy and angular momentum. Basically, it's not conservative. Oh, sorry. It's not balanced at each time. It's only balanced on average. So, right, because you're measuring the balance at infinity, and you're comparing it to the energy lost at the point particle, at this. So in this region there may be some deviation, and you have to take that into account. But the key thing is well, I'm going to be talking about doing it in the circular limit, and then we don't have to worry about those terms. So yes. Okay. So basically, if you do quasi-circular, you can make these two terms vanish. And also that the radiation of this FR is really small compared to the angular momentum radiation. So basically the dissipative effects are just captured by this f sub phi. And basically, right, so this f sub phi is just basically the luminosity divided by the gravitational frequency, or the angular orbital frequency. Yeah. Yes. So, right, anyway, so if you look at the papers, they write it like this. And then they say the complex strain, like what people have done is they calculate the multipolar sum of all the gravitational waves. And you can write it with the complex strain where this H plus IH cross can be written as like a sum over all the spin waves, zero harmonics. And then the luminosity at infinity looks like how much flux is escaping. It's basically looks like this. And then by calculating this script L, you can then just figure out how much energy you're losing and how your particle will plunge, or sorry, will inspire, like how quickly it will fall into. Yes. Right, and then okay, so yeah, and then in particular, like this dE dt is just minus the luminosity, and it's, you know, in the actual papers they do it a little bit more formally, where you can actually fully write this out in this form, and then this HLN looks like the Newtonian or the leading order effects. And then there's these other factorized tail terms where they try to figure out if there's any extra information with a similar like resummation process. And also they add some numerical relativity calibration here. And after you add all of these effects, you can get very good agreement. Yeah. Yes. So, okay. And then, okay, so here's what like an example waveform looks like. Basically, you can see that this is the amplitude of the 2-2 mode. And you can see that it starts to grow until it reaches a peak and then it goes down. And so but basically like the EOB, like this spiral model I was talking about is fitting all the way until like this inflection point. And then the frequency keeps growing because they attach the quasi-normal mode ring down to it. Yeah. So basically like at this point is when they attach it, the ring down. Yeah. So, yeah. Okay. So basically I think my takeaway is that the two-body problem can be mapped to an effective one-body problem. The key thing to realize is that you can improve the post-Newtonian Hamiltonian by smoothly connecting it to like the zero mass, or sorry, like basically when Q is really large, or when this mass ratio is really large, that these two things need to agree, and by forcing agreement, you can improve the waveform, and then you can write this as a system of ODEs and include dissipative effects and calculate what the waveform looks like for detectors. So yeah, and then things I didn't discuss. You can generalize this to a deformed curve metric to include spinning binaries, and you can also include processing binaries. One thing you also would want to do in practice is you want to do Pate resummation to make the EOB potentials and fluxes, make them improved. And you can, they also will have like a certain like pole at like the light ring. So people do carefully think about that. Also to calibrate to NR, there's a lot of other ways. There's another area where the EOB potentials also need extra calibration parameters in addition to these next to quasi-circular terms that I showed for the HLM modes. Yeah, and I didn't discuss attaching the ring down. Basically, you're basically fitting it by continuity and differentiability at that point. Yeah, and then also the calibration to NR. What people are saying is at basically at this peak right here, it needs to be agreeing with NR, where like the amplitude and the amplitude and like the phase need to have like the same agreement basically, and that's what they're calibrating to, so that the quasi modes will fit well. Yeah. yes, oops. And then also the detailed discussion of matching. You need to make sure that your Hamiltonian kind of is unique and that it's not equivalent with a canonical transformation. And then the simple example for how I computed how the real Hamiltonian and the effective Hamiltonian are related also is done in a much more complicated way with this like Delaunay Hamiltonian, or you can do it with scatter. But there's lots of ways of doing that. But people carefully thought about that. So if you look at the original papers, they're most going to be discussing this Delaunay Hamiltonian method. And then the references. So basically, there's these lectures by John Sanoff. Also, these EOB reviews by Demore are really good. So, and then there's also a lot of original papers that I cite right there, or the modern equivalents. So yeah, thank you very much. Let me know if you have any questions.
So you said that for the matching to ring down part or whatever, you try to match the phase and the amplitude at merger for the EOB part
Yeah.
to NR.
Yeah, you want to match like the modes, like so you're doing like basically like right, you're doing H. You're saying the 2-2 looks like A2-2. So there's kind of two types of matching. There's like the matching where it needs to agree at the matching point, but also they also have other parameters that are used for making the mismatch agree.
Yeah. I was gonna specifically ask about like dephasing throughout the entire inspiral part, because if you make it match at one of the two endpoints, then the other part is gonna be out of phase, and that changes like when your waveform merges and everything like that.
Yeah, I think there's like with the newest waveforms, there's maybe like 4 free parameters that they're matching, right? And basically what they're saying is like A22 at like TM is equal to NR, and then like basically the derivative of A22, and then like the phase, basically that T phi. Right. So there's a couple conditions like that, which are pretty important. And also there's and that's mostly for these like next to quasi-circular terms, because I think those next quasi-circular terms are really related to the fact that I was setting the center of mass momentum to be 0. So I think that this is what kind of like accounts for this effect. And then there's also some phasing terms that are also added. So
then for less than quasi-circular orbits, this breaks down a bit.
Yeah.
Are there other more terms that you add for the
I think
not quasi-circular part, or do people just not?
I think that the eccentric case is like actively being worked on.
Okay.
Yeah.
I imagine it's harder than the quasi-circular.
I think that they maybe, I'm not sure, but I know that like they just released an eccentric waveform, like the EOB group basically that did this. So because you need to be careful, like defining eccentricity, etc.
Any other questions? Let's thank our speaker again.
One other thing is they do have other flexes, like this that's the F sub r that I said was 0. That you can also like generalize that, and like that not being 0, I think will maybe account for other quasi-circular assumptions. I think I think maybe that's the other part. So